If I can't picture it, I can't understand it. Albert Einstein. Welcome students. Today in this lecture, we start discussion of methods of impulse and momentum and cover the area concept of impulse of a force and the impulse momentum principle. Till so far we have studied Newton's laws and methods of work and energy. Newton's law facilitates us a method to analyze what is happening at a point of time or at an instant, whereas methods of work energy facilitates us two things: what is happening over a space interval and how to quantify various kinds of energy conversion processes. Methods of impulse and momentum will facilitate us another important method, that is how to analyze what is happening over a time interval. Actually, this method facilitates us two things. The time interval may be a finite or the time interval may be infinitely small. Of course, when the time interval becomes infinitely small, this method provides the only way of solution. Consider this diagram. Here it is shown that a batsman is hitting a ball. And it is very well known that the contact duration of the ball with the bat is very, very small. And of course, we can say infinitely small. In that duration, how much force the bat has applied on the ball and how that force varied with time in that infinitely small interval, that idea is almost unknown. But two things we know: velocity of the ball before the hit and velocity of the ball after the hit. So we can calculate change in momentum of the ball. Actually, impulse momentum principle suggests us that impulse of all the forces acting on a body will be equal to change in momentum of the body. So here we can calculate impulse of the force of the bat on the ball, because we know momentum of the ball before the hit and momentum of the ball after the hit. And that impulse we can calculate even without knowing how the force of the bat on the ball was varied over this small interval time. So this again provides a very important method. Let us see what is there in method, and first we consider what is impulse and impulse momentum principle, and then let us see how these methods can be applied to analyze various physical situations. Impulse and impulse momentum principle. Consider a body of mass m in translational motion under the action of a force. If at an instant the force on the body is F vector and velocity of the body is V vector, Newton's second law suggests that F vector is equal to d by dt of mv vector. After a small mathematical manipulation, what we can write: F vector into dt is equal to d of mv vector. Now performing a definite integral over a time interval, what we can say: if in a time interval t initial to t final, velocity of the body changes from v initial to v final, we can write integral t initial to t final f vector dt is equal to mv final minus mv initial. Let us say this equation number 1, and that equation is impulse momentum principle. Here the quantity integral of f dt over a time interval is known as impulse and is very important. So let us first define what is impulse. The left hand member of the above equation is known as linear impulse or simply impulse of the force in the time interval concerned. Actually here time interval is t initial to t final. So if we integrate the force with time over the time interval of action of the force, the integral will give us a quantity that is known as linear impulse, or simply it is called impulse. So usually we call it impulse. Impulse is a vector quantity resolving the force F vector into its Cartesian components. We can write integral t initial to t final f vector dt is equal to I cap integral t initial to t final fx dt plus j cap integral t initial to t final fy dt plus k cap integral t initial to t final fz dt. So this equation we have written by resolving the force F vector into its Cartesian component fx, fy and fz. This equation also suggests a very important idea: how to convert integration of a vector function into integrations of scalar functions. That is also important because till so far in mathematics we have studied only how to integrate a scalar function. But here the integration of vector function was there. So we have converted into three scalar function integration. Now this idea is very simple, but let us see further. Denoting the impulse by a vector j, we can write j vector initial to final is equal to jx initial to final I cap plus jy initial to final j cap plus jz initial to final k cap. So we are giving notations to this large equation. So this is j vector initial to final. It is this integral is jx I to final. This is what jy I to final. This is what jz I to final. Each component of the impulse can be obtained either by evaluating the definite integral or area between the curve and the time axis by plotting fx, fy and fz against time t as shown in here in the diagram. See, this is how this diagram suggests how fx varies with time. So suppose here we have time interval t initial and we have t final. So either we integrate this function or calculate the area. So from t initial to t final, this shaded area is jx initial to final. Similarly for fy, so from t initial to t final, this area will be what? Y component of impulse, we denote it by jy I to f. And in the same manner, we can say about fz. So here t initial to t final, this area shaded is z component of the impulse. So here we can convert the impulse into area or definite integral. So whatever method you will find suitable, you can adopt. Either do this integration, or if graph is simple to draw the graph, or if the graphs are given, then directly measure the area or calculate area from the graph. Don't convert the graph into equation and integrate. So you can use both the way, either measure area or calculate definite integral. Impulse momentum principle. Now we come on the impulse momentum principle. We have already said what was the impulse momentum principle, but let us formally just give a statement of the principle. The idea conveyed by the equation 1 is known as the impulse momentum principle. That states, if a body is acted upon by a force, the impulse of the force in a time interval is equal to change in momentum of the body in that time interval. Of course, that idea we have developed for a single force, but it can be extended if several forces are acting simultaneously on the body. So that equation we are writing here, t initial t final, f vector dt is equal to mv final minus mv initial. When several forces act on a particle, the impulse of each of the force must be considered, and the equation becomes summation t initial t final f dt is equal to mv final minus mv initial. What this summation sign suggests that this integral is impulse of a force, and summation means total impulse of all the forces which are acting on the body. Actually, here we have said particle. I will mention very frequently that what is particle in mechanics. Particle is either a point mass or a body in translation motion. Because if a body is in translation motion, all of the points of the body have same velocity, same acceleration, and follow identical trajectories. So motion of the entire body can be represented by any of its particles. So if a body, irrespective of size, is in translation motion, it is considered as a particle. Denoting momentum by P, impulse momentum principle can be expressed as summation j initial to final is equal to P final minus P initial. So we have symbolized the impulse also and momentum also. So we can write the impulse momentum principle in a very small manner in this way. Or P initial plus impulse total initial to final is equal to P final. So this equation can be represented in this way also. Actually, this way gives us more physical insight. What? Body was having some initial momentum. Impulse of all the forces over a time interval, when added to the initial momentum, what we obtain? The final momentum. A strategy explaining how to apply the principle is shown in the figure. Here, consider a body that is moving with initial momentum. Pi initial is equal to mvi initial, and we add impulse of all the forces. So say this way. So this vector, this quantity will be vector, and we are representing this quantity as a vector. Summation j initial to final, or that is equal to summation t initial t final fdt. If you add this vector to that vector, what you get? Final momentum vector. So P initial plus this summation J initial to final, what you got here? Final momentum. This has been facilitated by triangle of vector addition. So this diagram suggests us two things. Either we can solve this equation analytically, or we can solve by using triangle of vector addition, or you can say geometrical method, or in other words, graphical method. Why you call this drawing a triangle graphical method? Because graph is defined any diagram drawn to a scale. And when we are representing a vector by arrow, by definition, what is that? A directed line segment drawn to a scale. So this diagram is also sometimes called a graph or graphical method. The above diagram, known as impulse momentum diagram, explains how to apply the principle geometrically, as well as how to write the equation required for analytical solution in Cartesian components or Cartesian symbol, or you can have polar symbol also, but just see what the idea is. When we have to apply the impulse momentum principle, I will suggest you to draw this impulse momentum diagram. Initially, it is very important because this diagram will suggest you how to apply the principle in the same way as we are studying Newton's law of motion. So initially, in every problem, if you draw the free body diagram, you'll write equation most correctly and you'll have no confusion at all. But later on, when you become expert in Newton's law, in some simple situation, we omit drawing the free body diagram. Similar fashion we adopt here. Initial, to apply the impulse momentum principle, I will stress to draw the impulse momentum diagram if physical setup is given. And when you become comfortable in applying the principle, you can omit this diagram from drawing, but still you have this diagram in your brain, in your mind. So P initial x is equal to summation ji to final x is equal to p final x. So this we can write in Cartesian component. That's equation we are symbolizing for x component. Similarly, pi y is equal to summation ji to final y component is equal to p final y component, and similarly we can write for z component. So in this way, by drawing this diagram, we can draw these three identical component equation. Of course, in this equation, I have put vector sign, but you can remove the vector sign and use plus and minus sign. One direction, you can assume plus, and opposite direction minus, because for a component, either x, y, or z, only two directions are possible, either in the positive direction or the negative direction. Now, after studying the impulse momentum principle and what is impulse, let us try to apply these things on some physical situations where the impulse momentum principle should be used. So I have said you, let us try to understand how to apply this principle. But before going to that, we have to understand what is the area of the impulse momentum principle, its application. I have told you in the beginning that to describe what is happening over a time interval is the area of application of this impulse momentum principle. Impulse momentum principle find its applications in analyzing situations that involve velocity change during a time interval. So we have seen earlier also in diagram, a batsman was hitting the bat. Of course, the time interval is infinitely small, but that event we can analyze by impulse momentum principle. The time interval may either be of finite length or infinitesimally small. So both kind of time interval we can account by using impulse momentum principle. Situations of finite time intervals can also be analyzed by a two-stage process. The first stage is to find acceleration using Newton's law, and the second stage is to find velocity change in the concerned time interval using ideas of kinematics. The impulse momentum principle combines these two stages into one stage similar to work energy. That is important idea when we are dealing problems of finite time interval. Actually, in finite time interval, all the forces at every instant can be defined very precisely. So at every instant we can define acceleration of the particle, and once we find acceleration of the particle, by using idea of kinematics in second stage we can calculate change in velocity over the given time interval. What impulse momentum principle does? It combines these two stages into single stage. It facilitates us to directly calculate change in momentum or change in velocity over a time interval. And that is similar to work energy. What work energy does? It combines again two-stage method. Instead of work energy, you can calculate acceleration. And by using idea of kinematics, you can calculate speed change over a space interval. So work energy does what? It combines that two-stage method, application of Newton's law and then application of kinematics into one stage. But that work energy principle does it for space interval. And here the impulse momentum principle combined the two-stage process into one-stage process for a time interval. However, for situations involving momentum change in an infinitely small time intervals, the force involved tends to acquire infinitely large magnitudes. Their relation with time remains usually unknown. These events are known as impulsive events. Here, the unknown nature of the force makes Newton's law unsuitable to use. The impulse momentum principle provides the only method to analyze such situations. Actually, this is another very important application of impulse momentum principle, because for the events of infinitely small time interval where there is finite change in momentum, these kind of events we'll discuss later are known as impulsive events. In these events, the nature of forces and how the forces vary with time in that infinitely small interval is usually unknown. So we cannot use Newton's second law. But in such situation, we know the change in momentum. So we can calculate the impulse. In this way, impulse momentum principle provides us the only method to analyze the impulsive events. Reference frames and impulse momentum principle. This is another very important idea, how the different kinds of reference frame will affect application of the principle, or in other words, how this principle will be used in different kinds of reference frame. Let us discuss here. The theorem is applicable in inertial as well as in non-inertial reference frames. It is applicable or valid all the frames. So what we do in inertial frame, let us see. To apply the principle in an inertial frame, consider the impulse of all the physical forces and change in momentum with respect to the inertial frame under consideration. So that is similar to work energy theorem, how the work energy theorem was applied in inertial frame. What we have done, we have calculated work of all the physical forces in the frame under investigation and change in kinetic energy with respect to the given frame. The same thing we do here. To apply impulse momentum principle in an inertial frame, what we do, we consider impulses of all the physical forces and equate it to change in momentum of the body with respect to the given inertial frame. But what we do if a non-inertial frame is given, that is simply we will consider the impulse of pseudo forces also in addition to impulse of the physical forces. To apply the principle in a non-inertial frame, consider impulse of the pseudo force in addition to that of all the physical forces and change in momentum with respect to the non-inertial frame under consideration. So in this way, we have seen how we can apply the principle in inertial frame and non-inertial frame. Now let us apply the ideas on some physical situation, or in other words, let us consider few examples. Example 1. A material body of mass 500 kg moving with a constant velocity in a free space, when acted upon by a force F vector is equal to 3t square I cap plus 5t j cap plus 8t cube plus 400 k cap Newton, comes to rest in 10 seconds. Determine velocity of the body before the force was applied. Of course, that problem we can do by Newton's law. What we do? By Newton's law, divide this force by mass and you will find acceleration. And then using idea of kinematics, you can find initial velocity. But what impulse momentum principle does? Impulse momentum principle combines these two stages. What? Finding acceleration and then using kinematics into one stage. Let us see how we can apply the impulse momentum principle on this situation. The situation at hand can be analyzed either by the two-stage method of Newton's law and kinematics, or by one-stage method of impulse momentum principle. In situation involving velocity change during a time interval, impulse momentum principle should be preferred over the two-stage method of Newton's law and kinematics. That is obvious fact, because when we are using two-stage method, it will require little bit more time to in solving problem. But if you use single-stage method, of course, initially you may find somewhat uneasiness, because we are so accustomed to use Newton's law that you start problem using Newton's law. But if you use this one-stage method of impulse momentum principle, you can save some time, because here that is a time interval is finite, so you can define acceleration. But what you will do when time interval infinitely small? We'll discuss such problem also, and at that time you realize that impulse momentum principle is better than Newton's law if time interval is given. Summation T initial T final F dt is equal to mv final minus mv initial. So what is suggest? 0 to 10, that is time interval. That is, I'm writing here force vector 3t square I cap plus 5t j cap plus 8t cube plus 400 k cap dt is equal to mv null vector minus mv initial. Why? Because finally the body stops, so v final will be a null vector. And now we substitute the values. For mass we substitute 500 kg. So what we get? Let us first do this. So here 3 I cap we can take common, 0 to 10 t square dt. Here 5 j cap we can take common, 0 to 10 dt. Here k 0 to 10 integral 8t cube plus 400 dt is equal to minus 500 vi cap, because this quantity will become a null vector. Now after solving this, we can find v initial, that is minus 2 I cap plus 0.5 j cap minus 48 k cap meter per second. Here use of impulse momentum principle does not provide much simplification or simplicity over the two-stage method, but we must practice where and how to use the method, because there may be some instances as impulsive motion where this will be the only method available. Actually, why I am stressing to practice this method over the two-stage method? There are two things. Of course, this method will save little bit of time, one thing, and there are situations as impulsive motion where this method will be the only feasible method to analyze those situations. So we have seen here that is the mathematical function of force was given, how we can apply the impulse momentum principle. Now let us see the next example. Example 2. A 10 kg block slides down a plane inclined at 37 degree with the horizontal. The coefficient of friction between the block and the plane is 0.25. What is the increase in speed during a time interval of 3 seconds? Of course, this problem you can also solve by using Newton's law. By Newton's law, you can find acceleration. And by using the equation of kinematics, you can easily find speed change. But we'll solve here this problem by methods of impulse and momentum, or we see how we can apply impulse momentum principle in this situation. So what we do, velocities of the block at initial and final instance are shown by v initial and v final. Of course, we cannot say the body is start because here which time interval 3 seconds is not given. It may be in the beginning or it may be at the end. So we assume initial velocity as vi and final velocity as vf. So here this block was here, initial velocity and final. Now intermediate stage, we draw the free body diagram. Free body diagram at an intermediate stage. So this block, we show the force mg, that is 10 kg, so 100 Newton. We are assuming acceleration to gravity as 10 meter per second square. So in all these examples, if it is not mentioned to take g 9.8 or 9.81 meter per second square, we usually assume g is equal to 10. And another force is normal reaction. So normal reaction will make angle 37 degree, line of normal reaction. And force of kinetic friction will be opposite to sliding, so in upward direction. So that is force of kinetic friction. We are denoting it by small f. Now using Newton's law, we can easily do the components here, say that is x and y. So these are the components, length. So this will be the x component, this will be the y component. So we can write the values. So this will be 80 Newton and this will be 60 Newton. Very easy. How? This is 100 cos 37 and cos 37 is 4 by 5. So you will get 80. Similarly, how it is 60? 100 into sine 37, and sine 37 is 3 by 5. So we get 60 Newton. Now if it is 80 Newton, it will be counterbalanced by the normal reaction. So normal reaction is 80 Newton. And once normal reaction is known, we can find the force of kinetic friction. Coefficient of kinetic friction is 0.25. So friction force will be 0.25 into 80. So it will be 20 Newton. So that idea, we have used Newton's law to find various forces. Now we use the impulse momentum principle. And of course, there is no motion along the y direction. So we have to consider only x component. So in x direction, forces are 60 Newton and 20 Newton opposite. So we have to consider impulses of these two forces only. Again, these forces are constant, so no need to find to integrate them. Just multiply the force by time interval, you get impulse. So how we can get? Applying the impulse momentum principle for the x component of the motion, summation j initial to final x is equal to p final x minus p initial x. So let us substitute the values. So here we have 60 into 3 minus 20 into 3. 60 into 3 minus 20 into 3 is equal to final momentum 10 vf vector minus 10 vi vector. So here we can avoid the vector sign. So what you get here, 120 is equal to 10 v final minus v initial. So what is change in velocity? V final minus v initial is equal to 12 meter per second. So in this way, we have seen how to apply the impulse momentum principle in such situations. Of course, it is very easy to solve this problem by Newton's law. But our purpose of today's lecture is to see how we can apply the method. Basically the new method, how we can apply. We have to learn these methods. Example 3. A box of mass m is equal to 2 kg rests on a rough horizontal surface where coefficients of static and kinetic frictions are mu s is equal to mu k is equal to 0.25. The box is acted upon by a horizontal force F, which varies with time as shown. So here the force, how the applied force varies with time is shown in the graph. This force increases linearly from 0 to 20 Newton in the first 2 seconds and then decreases linearly from 20 Newton to 0 in next 2 seconds. It means at t is equal to 4, the force will become 0 or the application of force is vanished. Part A. Find instant when the box starts sliding. Of course, this problem can also be solved by the two-stage method, finding acceleration in time interval given with the help of Newton's law and then using idea of kinematics. But you can see here, particularly in this problem, use of impulse momentum principle will provide you better solution. Let us see how it provides the better solution. Initially, force of static friction counterbalances the force F. Thus, there is no net force and hence no net impulse till an instant t1, when force F becomes equal to the force of limiting friction. Thereafter, the box starts sliding and force of kinetic friction begins to act. Actually, this idea we can also analyze by Newton's law, because initially when the force was applied, the block will not begin to move. The block will begin to move or begin to slide when the applied force slightly exceeds the force of limiting friction. And how we can analyze this idea in terms of impulse? Initially, when the force was applied, the friction also comes into picture, and both are equal and opposite, so their impulses will cancel. So the instant when force F exceeds the friction, it will have its impulse more than that of friction. So there will be net impulse and the body will become to gain momentum. And when the body starts sliding or body begins gaining momentum, we call this instant by T1. In figures, the free body diagram and graphs representing the force F and the friction are shown here. You can see that is we are drawing the FBD. So the block is placed on the horizontal floor and it is its weight mass 2 kg, so weight is 20 Newton. So normal reaction, and here the applied force, so friction force will act in this direction. So if the weight is 20 Newton, normal reaction will also be 20 Newton. And the friction force will be what? Less than or equal to mu into 20, and mu is 0.25. So how much it will be? It is 20, so it will be 5 Newton. So how we can apply 20 Newton into 0.25, that is 5 Newton. So this 5 Newton is the limiting friction. Now we draw the graphs. Here we have x and y component. So actually there is no motion in the y component, so we have to only account for the x direction of motion. So here is the graphs, how the forces are varying. So how the force F varies is given, and how the friction force will vary in this way. Initially friction force will increase and opposing the force F. At instant T1, when this friction force will acquire its limiting value, the block starts sliding, and thereafter the friction force will become constant and equal to its kinetic value. So here let us see this page color. This shaded area will be equal to impulse of the applied force. Similarly, we show the impulse of the friction by sky blue color in this way. So what the shaded area represent? This color, impulse of F, and sky blue color, impulse of friction. Now what we do? Since friction opposes the force F, to subtract the impulse of friction, the graph of friction is flipped vertically as shown in the next figure. Now we have to subtract this sky blue area from this peach area. So the simple way is what? To just flip this graph vertically. So in this, so we have flipped this graph here. So now this area, you can see this area of, will be cancelled because opposite to that, and only this area will be remaining. So this is positive impulse and we represent by this peach color, and this area will be negative impulse because in this time interval only friction, here friction is there, but here in this time interval friction and applied force also there. So by substituting we have this area as a negative impulse and we show it by sky blue color. So that is positive impulse and here a negative impulse. Now in this way we can easily calculate the net impulse. So here this is what? This is net impulse till that time and this is net impulse in that time. So now the first question was find the instant when the box starts sliding. So we can easily find here by this instant T1, and from graph we can read T1. So T1 here value is 5. So you can see here that that is 0.5 seconds. Again you see the shaded area, that is net positive impulse, and here what? Sky blue, net negative impulse. And I have explained you why it is net, because the impulse of friction has been subtracted. So that is net positive impulse, it is net negative impulse. From the graph we can read when the block starts, that is this T1 0.5 second. How we can say? Because this value will be 5 and because it is given the limit friction is 5 Newton. So when force is 5, the time will be 0.5 seconds. So T1 is 0.5 seconds. So after the force F begins to act at t is equal to 0, at t is equal to 0.5 second, the block will start sliding. Find the maximum velocity acquired by the box. Of course, you see the first part. You will not find much more simplicity of impulse momentum principle over the Newton's law. But in this part, if you try to solve this part by Newton's law, you'll really realize that impulse momentum principle provides here better solution. See, we have redrawn the second figure, that is here the figure showing the net impulses. Speed of the block will keep on increasing till net positive impulse ceases to act at the instant t2. Let me call this instant t2. Now, till there will be net positive impulse, speed of the block will keep on increasing. And when the speed of the block or momentum of the block will keep on increasing, its speed will be increasing. So when the increase in momentum ceases, at that time momentum will be maximum or velocity will be maximum. So at this instant velocity will be maximum, and that we can apply by impulse momentum principle. So from the graph we get t2 is equal to 3.5 second. It is very easy because again you can see this was 0.5, so this will be 0.5, so 4 minus 0.5, so t2 is 3.5 second. Applying the impulse momentum principle for the time interval t1 is equal to 0.5 second to t2 is equal to 3.5 second, we get the maximum speed Vmax of the block. So here, because impulse is acting in that time interval, so we consider that time interval t1 to t2. P initial x component summation j initial to final x component is equal to p final x component. So P initial at t1 was 0. So, and what is this net impulse? This area of this peach color triangle. So height is 20 minus 5, 15, and this base is what? From 0.5 to 3.5, 3 seconds. So it is half into height, 15 to 3 is equal to mass into Vmax. So this is final momentum. So in this way, we can directly write what is the maximum velocity. So Vmax is 11.25 meter per second. So you can see how simplicity, with what simplicity we have obtained solution here by using impulse momentum principle. So let us see the next part. How long after the force begins to act will the block or box comes to rest? Means when the force was applied, how long after that instant the box will come to rest? Because we know that at t is equal to 4, this force ceases to act. Thereafter, there will be only friction. So the momentum of the box will reduce and ultimately it will stop. So how it will stop and when it will stop, we'll again calculate by Newton's second law. What we can see? At this instant, we know the momentum by this way. By multiplying this by velocity, we can know the momentum as t2. So let us suppose at time t3, the box stops. So till from t2 to t3, what is the impulse, this negative impulse? That should cancel the momentum at this instant. So let us apply this here. After acquiring the maximum speed, the block slows down and finally comes to rest at the instant t3 due to impulse of the friction. So we assume when the block will stop or the box will stop in instant t3. Let us show you here this way. So how we can write here? Applying the impulse momentum principle for the time interval t2 to t2 3.5 second to t3, when the block comes to rest, we get the instant t3. So from this interval to this interval, if we apply the impulse momentum principle, we know everything. Only t3 is unknown. What? We know the initial momentum, that is this velocity multiplied by the mass, and we know the final momentum, that is 0. And of course, this negative area we can express in terms of t3. So in that equation, the only t3 will be an unknown, so we can calculate it very easily. So pi initial x component plus summation of I to final impulse x component is equal to P final x component. So let us substitute the values. So this will be what? 2 into 11.25 initial momentum plus area of this sky blue trapezium. So what is area of trapezium? Half into sum of parallel sides. What parallel sides? T3 minus 4 plus T3 minus T2 means 3.5. So that is in this curly bracket we have sum of these parallel sides and into distance between the parallel sides, that is 5. So we have this formula of area of a trapezium. And what is final momentum? 0. Now you can see in this equation only unknown is T3, so you can calculate T3. So this will be 22.5 minus half 2t minus 7.5 into 5 is equal to 0. So here T3 is equal to 8.25 seconds. So in this way we have obtained finally when the block will stop the moment T3 by using impulse momentum principle. Now I suggest you to analyze this problem by using Newton's law. You can find or you can then feel what simplicity this method of impulse momentum has provided in this problem. So at present, I will not recommend you to learn this method because this method will be simpler than Newton's second law and use of kinematics. I will recommend you to enjoy learning a new method, and later on it will, depending on a level of understanding, you will be in better position to decide whether to use the two-stage method and whether to use this impulse momentum principle. Example 4. A ball of mass m is equal to 0.5 kg moving with 10 meter per second in the positive x direction of a gravity-free space is acted upon by a force F1 in the negative x direction and a force F2 in the positive y direction. The forces varies with time according to the given graph. So the graph is given here. So force in Newton and time in second. So this force is F1 shown in red color and force F2 is shown in blue color. F2 acts in positive y direction and F1 acts in negative x direction. Now again one thing, when force time graph is given and we have to find change in velocity, again use of impulse momentum principle will be simpler if it is easy to find area from the force time graph, means impulse from the force time graph. What the A part of the problem is, find velocity of the particle at the end of third second, means here, when these forces ceases to act. The impulse momentum principle or impulse momentum diagram for the given time interval is shown here. So that is the initial momentum pi vector, this 5 cap. Now we show the impulse of both the forces. So impulse of F1 will be in negative x direction. See, impulse of F1 we denote it by J1 minus I cap 0 to 3 F1 dt. And this integral show the area of this red graph, the area between this F1 graph and time axis. Similarly, impulse of F2 will be in the positive y direction, so it will be shown upward. So here J2, this integral J 0 to 3 F2 dt. So this is what? Impulse vector of force F2. And sum of these two will be equal to final momentum. Let us suppose the velocity vector happens in this direction. So this P final. So what we can write here? 0.5 into V vector. V vector we denote by final velocity. Now we can do the component of this xy component. We can write here x component of momentum and y component of momentum. Of course, we don't know the angle, so we will not write here the value. Simply we written Vx and here Vy. Now what the idea is, we apply the impulse momentum principle for the x component as well as for the y component separately. Impulse momentum principle for the x component, P initial x plus summation j initial to final x is equal to P final x. Let us substitute the values. So P initial x is what? Plus 5. And is what? The area of this red graph with negative sign, we can see the area. That is what? 4 into 1, 4, plus 2 into, that is 2, 4. So it is 8. So what we can write here? 5 minus 8 is equal to 0.5 into Vx. So here this value. From where we can easily write what is Vx. So Vx is minus 6 meter per second. So velocity of the body in x direction has been reversed and become 6 meter per second in negative x direction. Now we apply the impulse momentum principle for y component. Impulse momentum principle for the y component. So Piy plus summation Gi to final y component plus P final y component. So this quantity was 0, you can see from here. And this quantity we can find area of this blue graph. So that will what 1 into 2, that is 2. And what is that this area? That is 1 is here, and again that is 1 is here. So we can write the area. So relative substitute value 0 plus 4 equal to 0.5 into Vy cap. So what is this area? We calculate for how this area is that is 1 into 1, 1, 1, 2 and 3, and half of 2 is again 1. So this area is 4. So 0 plus 4 is equal to 0.5 Vy. So Vy is 8 meter per second. So we can easily find the y component of velocity also. Now we can write the velocity vector. Velocity of the ball at the end of third second is v vector is equal to vx I cap plus vy j cap. So we can write it in vector form. So v vector is vy I cap plus vx j cap. So here there is a misprint. So read it vx I cap and vy j cap. Let's substitute value here. That is minus 6. So it is minus 6 I cap plus 8 j cap meter per second. So in this way we have found the velocity. Please take care of here. There is a misprint. It should be vx. Now what is the next part B? Find the instant when x coordinate of the ball achieves its maximum positive value. Now we can analyze it. When x coordinate will achieve its maximum positive value, when x is maximum, its derivative will be 0. So dx by dt will be 0. It means at that instant, velocity x component must be a null vector, or speed of in x direction should be 0. So momentum component in x direction should be 0. So here again we can analyze this problem by using impulse momentum principle. Let at an instant t the x coordinate of the ball be maximum positive. At this instant, the x component of velocity, hence the momentum, both must be null vectors. So that I have explained you why they should be null vector. And now this suggests us how to apply the impulse momentum principle. Means final x component momentum is 0 and initial was given. So impulse in the x direction opposes the initial momentum. Therefore, the impulse in the time interval 0 to t must be equal to in magnitude to the initial x component of momentum. So that is very important idea. We assumed at time t that the x coordinate achieves maximum value. So in that time interval, actually initial momentum was in positive x direction and impulse of the force is in negative x direction. So this impulse will reduce the momentum of x component. So when the x component of momentum will become 0, we have to explore that instant. So at that instant, the impulse gathered in the x direction must be equal to the initial momentum. And this we can explore very easily by the given graph. Impulse momentum principle for the x component, Pix plus summation Ji to final x is equal to P final. Let us substitute value. What? 5 minus 0 t f1 dt is equal to 0. So this will what? This area must be equal to 5. So we can see in the graph. So this is what? 5. So area of the f1 t graph should be 5. And now we can explore. Area of the shaded portion in the adjoining figure must be equal in magnitude to the initial x component of momentum, that is 5. So in this graph, so you can see till 1 second area is 4. So before 1 second this will not happen. So it will happen after sometime after 1 second, say at time this t we are assuming here. So this shaded area must be equal to 5. So how we can calculate here? So 4 into 1 of this portion, and this was 2 into and this width t minus 1. So that is area of this shaded portion. I will explain again why this 4 into 1, because this width is 1 and this is 4. So this part is 4 into 1 and this part is what? Height is 2 and width is t minus 1. So this, And by solving this, what you get here, t is equal to 1.5 second. So after beginning of the forces, at t is equal to 1.5 second, the x component of momentum of the ball will be 0. It means at that instant, the x coordinate of the ball will have its maximum positive value. So because we are assuming that the ball initially was at the origin, that's why I'm saying maximum positive value. Now let us see the next example. Example 5. Here a setup is given. What setup is? Here is a block A of 8 kg, and this is a horizontal frictionless plane. And here is the block B of 3 kg, and they are connected by string and pulley. Strings and pulleys are ideal. So here a force F was applied. Value of force F will be given in the problem. Let us see what the situation is and what is asked. The arrangement shown is held motionless. A constant horizontal force F is equal to 150 Newton begins to act on the block A. Find the instant when the block A acquires a speed of 4.5 meter per second and tensile force in the thread. These two things we have to find. Of course, this problem you can also analyze by using the two-stage method. First, finding accelerations by using Newton's law. For that, you have to incorporate constant relation, and you can find acceleration of block A and acceleration of block B. Now you can find the time when speed of the block A will become this by using that acceleration and idea of kinematics. And by using the equation obtained in Newton's law, you can find tangent also. So solving this problem by Newton's law is not very difficult. Again, I'm not saying that impulse momentum principle in this problem will provide great simplicity, but I will again mention over and over again that here the today's purpose is to learn this method, and it is up to you that where you use this method, decide later. But there will be one instance, especially impulsive event, that I will discuss later in detail what is impulsive event. First, I will take an example of an impulsive event, and then I will discuss in detail what is impulsive event. In an impulsive event, the impulse momentum principle will provide the only method of solution. So if there is an area where this method provides only solution, so it is necessary to learn this method. And learning a method is what? Most simple to apply this method in those problems which you can solve by other methods too. So you have better insight. So regarding this situation, you can solve it very well by Newton's law. I'll suggest you also to solve it by Newton's law just for practice. But here we'll see how we can apply the impulse momentum principle in this situation. Constant relation. First we explain the constant relation because velocity of the block and velocity of block B will have some relation. By visual inspection or any other suitable method, we can write. So what is visual inspection? If you shift the block A by an amount, the same amount, this string will be lengthened here and lengthened here. So by double amount, the block B will rise. So what is velocity of block A? Velocity of block B will be double of that. So VB is equal to twice of VA. And moreover, if we assume VA in this direction towards left, VB will be upward. So if V is towards left, VB will be upward. So that is constant relation, that magnitude relation as well as direction. Denoting the tensile force by T, we can draw the impulse momentum diagram as shown. And we know that all the forces will be constant because F is constant, so T will be also constant. So to calculate momentum, there is no need to integrate. We simply multiply the forces with time interval. Impulse on the block A, that is impulse IMP, that is impulse momentum principle. So in short, I will mention wherever I write impulse momentum principle, I will write capital IMP. So on block A, that is initial momentum 0. Then we show the impulse, that is block A plus pulley. So impulse of this force F, that is F delta T. So delta T, I am denoting the time interval. And here will be T delta T and T delta T. So these impulses are acting on the block A equal to final momentum. We are assuming the velocity of block A in this way. So what will be 8 VA? So it will be 8 VA. That is impulse momentum diagram. And based on this impulse momentum diagram, we can write the equation. what xy component we can say. So there is no need to write equation in y component, only x component. So pix summation fi to final x is equal to p final x. So in this way, what is p initial x component? 0. What is impulse? ft delta t means 150 into delta t minus 2 into t delta t is equal to 8va caps. So 8va. So we can write here. So 0 plus f delta t minus 2t delta t is equal to 8va. Now for f we can substitute the given value 150. So what we write here? 150 delta t minus 2t delta t is equal to 8va. See equation number 1. Now we apply the same the principal impulse momentum principle in the similar fashion on the block B. So first we draw its impulse momentum diagram. Impulse momentum principle on the block B. So impulse momentum diagram, initial momentum was 0, so we'll show it here, plus impulse of all the forces. Here forces acting are tension T and mg. So here impulse of T delta T and mg. Mass is say 3 kg, so mg will be 30, so here will be 30 delta T. And we have assumed that the block A is moving in this direction, so block B will move upwards, so its momentum will be here 3vb in this way. Again one thing, suppose if block velocity of block is found in that way towards right, so automatically we'll get minus sign. So we can write here with the help of this impulse momentum diagram, we write the equation. So what will be equation? P initial y component summation I to final y component is equal to p final y component, because here motion is in y direction only. So initial momentum is 0 and impulse is t delta t minus 30 delta t. So t delta t minus 30 delta t is equal to 3vb. So this is equation number 2. So t delta t minus 30 delta t is equal to 3vb, equation number 2. Now what we can solve? I will leave you the algebraic simplification for you. By incorporating this relation constant and these two equations, we can find the solution. Employing the constant relation and VA is equal to 4.5 meter per second, that is given here. Then solving equation 1 and 2, what we get? Delta t is equal to 1 second. So in this way, we will find what is value of delta t. Again, of course, we can argue that here the impulse momentum principle is not providing greater simplicity or Newton's law. So why we learn? Actually, our purpose is at present not to decide which method will be better. Our purpose is first you have to learn this method. So I'm using all kinds of, I'm taking here all kinds of example. We are taking those examples which can easily be solved by Newton's law. So you can compare what is the difference between method and where this method is better. And we'll take some other situation where this method cannot be applied. As I mentioned earlier, those are called impulsive events. So let us take B part and again, what is B part? Tensile force is also asked. So here by these two equations, we can find tensile force also. So this is becoming 57 Newton. So in this way, we have solved the entire problem. Now let's come to the next situation here. Example 6. A block of mass m is given an initial horizontal velocity v0 on a horizontal floor that is lubricated with an oil. The force of viscous drag from the lubricating oil or from the floor on the block is proportional to velocity of the block. If the constant of proportionality is k, find the distance slid by the block before it comes to rest. Again, this problem we can solve by finding acceleration. Of course, here acceleration will not be constant, acceleration will be variable. So you can use the idea of kinematics by integration process. You can find how much distance the block will travel. But let us see how the impulse momentum principle can be used here in this problem. So the situation is given here, horizontal floor that is lubricated. So and block initially given a velocity v0, and as the block will slide, the lubricating oil will provide a viscous drag, viscous friction, and that friction is proportional to velocity of the block, and constant proportionality is given to be k. So how we'll proceed here? Since the motion of the block remains unidirectional, the distance slid is equal to the displacement of the block, denoting time in which the block remains in motion by tau and velocity of the block by v vector. The distance delta x slid before the block comes to rest is given by this equation. Again, this is very important idea. Actually, we know that direction of motion of the block will not change, so its displacement will be equal to distance. So here I am writing displacement. Displacement is what? Integral v dt. So we can write that is distance also. So integral v dt is equal to delta x. Let us call equation number 1. That is what basic idea. Now we apply impulse momentum principle. For that we draw the impulse momentum diagram and basically we show all the forces acting on it. The impulse momentum diagram can be drawn as initial momentum mv naught plus all the impulses, impulse of gravity, impulse of normal plus impulse of viscous drag. So impulse of gravity mg tau, because it is constant, so we multiply by tau. Normal reaction will also be constant, so there will be n tau, that is impulse of normal reaction, n will be equal to mg, so mg tau. So these two impulses will cancel at every instant to each other. Now here we have, this is a variable force, so we cannot multiply with time, so what we do, minus 0 to tau kVdt is equal to, that is the final momentum, that is 0. So what we can write here, mv naught minus integral kv dt is equal to 0. So let us apply here, that is x and y component. No need to write anything in y direction, only x direction. So p initial x component plus summation j I to final x component is equal to p final x component. So its value is mv naught positive, its value is minus 0 to tau kVdt. Now we can take outside of integral because k is constant. So that is vdt is equal to mv naught by k. This is very simple to write. Now by this equation, that is delta x. So we can write delta x. From equation 1 and 2 we get delta x is equal to mv naught by k. Now you can see how simple solution was with the help of impulse momentum principle. And if you use the two-stage process of using Newton's second law to find acceleration and then lengthy integration in kinematics, you can realize that here impulse momentum principle finds a better way of solution. Again, today's talk is not concentrated on to decide where this method will be better and Newton's law method will be not better than this. The purpose of today's talk is to learn this method. And as you apply this method in several problems, you will again automatically gain an experience to decide where to use this method and where to use the two-stage method. Example 7. A ball of mass m moving horizontally with a velocity u is struck with a bat. As a result, the ball starts moving with a velocity v at an angle of theta above the horizontal as shown. So here this is given. A ball was coming with velocity u, it is struck by this bat, and after the hit it starts moving with velocity v, and angle of velocity v is theta above the horizontal. So that diagram was given. We have to find part A. Find an expression for the average force exerted by the bat if contact duration is delta t. Again, in the beginning I have mentioned that in this hitting kind of process or impulsive event, how the force varies with time is usually or almost unknown. So what is asked here? Average force. So we represent that variable force in very small time and variation by a constant equivalent. So what is average value? Actually, average value of a variable is equivalent constant value of that variable. So if you say average force means we represent by it constant force, and contact duration is delta t. So we have to find expression for this average force. Of course, we assume usual notation. This vertical is y and this horizontal towards right x. So how we proceed? Denoting the average force exerted by the bat by F, weight of the ball by mg, and contact duration by delta t. The impulse momentum diagram is shown in the figure. First we draw the impulse momentum diagram, and then let us see how to write the impulse momentum equations. So impulse momentum diagram, initial momentum is mv vector towards right plus impulse of all the forces. Forces acting on the ball during the contact with the bat are its weight and the force exerted by the bat. So here the ball, I'll assume this force by the bat in this direction. So by represent by F, We are assuming average value, so as a constant, so impulse will be F delta t. And gravity will act downward, so it is impulse of gravity mg delta t. Now that is final momentum, P final is mv vector or mv simply. So we are represent here x and y direction. Now with the help of this impulse momentum diagram, we can easily write the x and y component of impulse momentum equation. So here we resolve this x, we don't treat this x component fx dt and y component fy dt. Because we represent this as constant force, average force, so this will also be constant, this will be also constant. So we can write these impulses component. Similarly here we write here mvx or p initial x and p final x. So it will be what? And if we assume this angle theta, because angle theta is given, so Vx will be what? V cos theta. So it will be what? Mv cos theta. And similarly it will be Mv sin theta. Now with the help of this diagram, we can easily write the impulse momentum equations. Impulse momentum principle for x direction. P initial x plus summation I j I to final x is equal to P final x. So P initial x is minus mu plus fx dt is equal to mv cos theta. Very simple, right? So minus mu plus fx delta t is equal to mv cos theta. And from here we can write fx. Fx will be what? M in common, u plus v cos theta upon delta t. So that is x component of force. Now by writing impulse momentum principle equation in y direction, we can find y component of force. So what it will be? Initial momentum is 0. And the impulse is what? This impulse Fy dt minus mg dt is equal to this momentum. So equation, formal equation is what? P initial y component plus summation j initial to final y component is equal to P final y component. Value of this you can see from here 0. And this is what? Fy delta t minus mg delta t. So 0 plus Fy delta t minus mg delta t is equal to mv sin theta. Now we can realize the importance of the impulse momentum diagram, because if you draw the impulse momentum diagram, you can substitute this value very easily. There will be no error in substituting any of the values. And by solving this equation, we can easily find Fy. So Fy will be mv sin theta upon delta t plus mg. So now we have obtained fx component and fy component. Of course, please write it fy because here is mistyping. So fy will be mv sin theta upon delta t mg. So the average force exerted by the bat, now we can write in vector component what? Fx I cap plus fy j cap. So f vector will be what? This mu plus v cos theta upon delta t I cap plus this mv sin theta upon delta t plus mg j cap. So in this way we have found expression for the force. Now our purpose of this problem is to explore what is an impulsive event. Of course here we have not mentioned the value of delta t. Now we take some values of delta t, values of mass and velocities, and let us analyze what we can explore here in this impulsive motion problem. Find the average force exerted by the bat on the ball for contact duration delta t is equal to 300 millisecond and delta t is equal to 3 millisecond. Mass of the ball is 150 gram. Speed of the ball before and after the hit are u is equal to 20 meter per second and v is equal to 35 meter per second respectively. The angle theta is 37 degree. Acceleration of free fall is 10 meter per second square. These data is given, and we have to consider these two contact duration, 300 millisecond and 3 milliseconds. Of course, you can say 300 milliseconds means 0.1 second, also a, you can say, an impulsive event, but 3 millisecond will be more approximate, or we can say more close to an impulsive event, because how we are defining an impulsive event, duration of the event must be infinitely small. So smaller is the time interval of contact, better it will be an impulsive event. So let us see how we solve this problem. Again, we have obtained the expression. We have to substitute the values given. So the expression of force, average force, what is that? F vector is equal to mu plus v cos theta upon delta t I cap plus mv sin theta upon delta t plus mg j cap. That expression we obtained, and we have to only substitute the values. For the contact duration, delta t is equal to 300 milliseconds. So what the force is? That is 0.15 mass and 20 plus 35 cos 37 upon 0.3 I cap. That is this mass in gram has been converted into kilograms. So this now for j component we substitute values. Again 0.15 into 35 sine 37 upon 0.3 plus 1.5 j cap. Here 300 millisecond is converted into second 0.3. Now we substitute, we have substituted the values and calculate the values. So it will be 24 I cap, this is 24, and this term will be 10.5 plus 1.5. Now you can compare. That 1.5 Newton cannot be neglected as compared to 10.5 Newton. So we can, we'll write here 24 I cap plus 12 J cap. This sum will be 12. So that is the average force for this contact duration. Now you see for 3 milliseconds. For contact duration, delta t is equal to 3 millisecond. So this force will be, again, this numerator will be same, 0.15 into 20 plus 35 cos 37 upon 0.003 I cap plus 0.15 into 35 sine 37 upon 0.003 plus 1.5. Again, we have converted this 3 millisecond means 3 upon 1000 seconds, so 0.003. Now we substitute values. Only what we'll see here. This will be 2400 I cap. This will be 1050 plus 1.5 J cap. Now you can see the difference. Here, in this situation, as compared to Y component of the force exerted by the bat, the gravity cannot be ignored, but here it can be ignored. That is a very important idea. So we write it approximately 2400 I cap plus 1050 J cap. Just see what we can draw information from this calculation. That is, smaller is the contact duration, smaller is the effect of gravity as compared to that of the force exerted by the bat. So that you can see means if you make even contact duration much smaller, this will increase because dt is here, and this will remain constant. So smaller is the contact duration, smaller is the effect of gravity as compared to the reaction force of the bat, and we call the reaction force of the bat as impulsive force, and gravity is a finite force. So in case of impulsive events, what we do, if contact duration is exactly almost tending to zero, effect of all finite forces we can ignore, and we have to account only the effect of all the impulsive forces. For a typical contact duration of 3 milliseconds, the effect of gravity becomes negligible as compared to the force exerted by the bat. Here we can see this idea. Now with this example, we are in a better position to understand more about impulsive event. So we'll discuss about what kinds of events are called impulsive event. So we have seen that in impulsive event, momentum of a body changes by finite amount in an infinitely small time interval. And what we mean by infinitely small interval, it is not absolute zero. Actually, an event will be called infinitely small if duration, if that duration is negligible as compared to other durations concerned in the problem. So let us see situations where momentum changes by a finite amount in an infinitely small time interval. The forces responsible have infinitely large magnitudes. These events are known as impulsive events, and the forces are known as impulsive forces. So we have seen what kind of event we can say impulsive events, or usually the duration of impulsive event we ignore and will assume always to be zero unless it's not specified. All kinds of collisions are typical examples of this category of events. Any kind of hitting problem, collision problem will be example of this impulsive event. Impulsive forces. Now, the reaction forces which are responsible for this finite change in momentum in this infinitely small time interval are called impulsive forces. So here in the previous example, the force exerted by the bat is an impulsive force. But gravity is not an impulsive force. Reaction forces that are responsible for the change in momenta of the body participating in an impulsive events are known as impulsive force. So I say momentum is there will be, of course there is force, there must be two bodies. So momenta, both the bodies may change. So the forces which are responsible for the change in moment of the body, basically they are reaction force between the bodies, they are called impulsive forces. And their magnitude tends to be infinitely large because time interval we are assuming negligibly small. Again, how these forces vary in that infinitely small time interval is almost unknown or usually unknown, but still we are able to define the force average value and effect of the force as we have seen in the previous problem. How their magnitude vary with time is usually unknown, but their impulse that is equal to the change in momentum is known. So that is what advantage here. Duration of an impulsive event is considered to be negligibly small. Therefore, the magnitude of an impulsive force tends to be infinitely large in order to produce finite impulse to provide finite change in momentum. So that is idea. Again, I have explained here why the magnitude of this impulsive force will become infinitely large. The unknown nature of the impulsive forces makes the Newton's law unsuitable to analyze an impulsive event. The impulse momentum principle provides the only method to analyze such situations. Here, that is advantage, biggest advantage of the impulse momentum method over Newton's law. Because in impulse events, how the impulsive forces vary with time during the duration of impulse event, it is usually unknown. So we cannot use Newton's law. The only way is what? To use the impulse momentum principle. Non-impulsive forces. Again, here we have defined impulsive forces, so it is very important to define non-impulsive forces. And with the previous example, we can see all finite forces in an impulsive event will be what? Non-impulsive forces. Finite forces means the forces, in a very crude language, I can say, value of which is known or which have bounded value, not unbounded value. They are called non-impulsive forces. So in the previous example, gravity was impulsive force, non-impulsive force. All finite forces, I forces of bounded magnitude, are known as non-impulsive force in an impulsive event. Actually, the term impulsive force and non-impulsive force is applicable only for impulsive events, not in general. Impulsive or impulse of a non-impulsive force in an impulsive event remains negligible as compared to that of impulsive forces. That is, again, we have to ignore the impulse of non-impulsive forces. Means we will not count these forces. Means which forces? Which are non-impulsive. And with a very broad idea, we can say all finite forces will be classified as non-impulsive force in an impulsive event. Now we have learned what is an impulsive event. Let us further extend the idea. Here a setup is given. Now a particle is there. You can say a disc or a ball that is tied to a light thread, and that other end is fixed to a nail A and the point B, and distance between A and B is L. And of course, length of thread is larger. It is given in the problem 2L. Let us see what is the other information are given. A light inelastic string of length 2L is tied at one end to a fixed nail A on a frictionless horizontal floor. A particle of mass m attached to the other end of the string is placed at point B as shown. The particle is given a velocity u by a sharp hit perpendicular to the line AB. So that is shown here. So this velocity u is given to the particle by a sharp hit. Sharp hit means a hit of a very small duration. So this velocity u is given, and u is perpendicular to this line AB, and this distance L, and total length of thread is 2L. What is asked? Determine speed of the particle immediately after the string become taut, an impulse of the tensile forces of the string during the process, means when the string becomes taut, that is process. Actually, the ball will go here, the string will apply no force initially till it becomes straight. The moment the string becomes straight, it will not apply any force, but thereafter the string will apply a force, and in a negligibly small time the ball direction of velocity will change, and thereafter the ball will keep on moving in a circle of radius 2L. So that transition process, what velocity of the ball becoming some other perpendicular thread, say we denote that velocity by v from u, that transition process is called here this process. So during that process, what is impulse of tension? Actually, during that process, this process of very small time, so we will call it impulsive process. Again, please take care of this diagram is top view because this setup is on a horizontal floor. Gravity is not vertical downward, gravity is what here into the plane of figure. So gravity will always be balanced by normalization of floor, and there is no friction from the floor. So only force acting to control the motion of the ball or particle is the thread tension. So let us proceed further here. Till the string becomes straight, no force acts on the particle parallel to the plane. Thus, particle moves on the straight line BP with a constant velocity u. So, till the state becomes straight, the particle will keep on moving on the line B. Suppose where the string becomes straight, we denote that point by P, and so we call this line VP. When the string becomes taut, it makes an angle of 30 degree with the line BP. Immediately after this, the particle begins to move on a circular path of radius 2L with a velocity v as shown in the figure. So we have shown here. So from B to P, the particle will keep on moving with the constant velocity v, and just here the string becomes straight, and immediately after that this particle will keep on moving with velocity v on a circular path of radius 2L. Now it is common practice. If you do this experiment, what you find, if you hit the ball here, at that point the ball will jump somewhat in this way. It will not follow a circular path because the thread you take is not perfectly inelastic. Actually, there is no material which can be treated as perfectly inelastic or perfectly elastic. Of course, the thread will have some elasticity. Because of that, this ball will jump on this side, so it will not follow a circular path. But here we are taking considering inelastic thread, so it will follow a circular path. And how it will follow a circular path, why it will follow a circular path, and what will happen if the thread were elastic, we'll discuss after this problem. At the point P, the string becomes taut and a change in velocity, hence in momentum, of the particle occurs in a negligibly small time interval due to the impulse applied by the impulsive tension in the string. So that is the key idea. Now we are in a situation to apply the impulse momentum principle at this instant. Denoting the impulse of the tensile force at P by J subscript T, the impulse momentum diagram is drawn here. So initial momentum is this. Initial means when the string becomes taut, this black lines show the string. So here the angle will be 30 degree, that is direction of string, and momentum initial. And impulse of string tension will be applied in the particle only here, and that will be along the string, so this way, and that is circular path equal to final momentum, that will be along the circular path, tangent to circular path. So angle between MV and JT will be 90 degree. Now that is impulse momentum diagram. So we can resolve it into X and Y component again in circular motion. It is X and Y, basically we have to denote tangential normal. So that is normal direction, is tangential. Again, if we saw X and Y, so we have to orient our coordinate system in such a way that we have to resolve as minimum vectors into their component as possible. So this orientation, one along JT and one along MV. If we see XY orientation this, we have to resolve only MU into its component. So we will get simpler equation. Suppose you take x here, y here, again you will get solution. But in this situation, we have to resolve jt into component and mv into component. So jt, you will find two components, x and y, then you have to square them and add and take a square root, then you will find jt. So problem length of solution will become increased. So how to orient the coordinate system, we have learned in Newton's law. That is, again I am reiterating, the orientation of coordinate system should be chosen in such a way that a minimum number of vectors should be resolved into their components. So let us see here how we proceed. This resolve component, so this will be mu into cos 30, so root 3 by 2 mu, and this will be this half mu sin 30. So only this vector mu you have to resolve into component, so we resolve it. Now impulse momentum principle for x direction. So what? P initial x plus summation j I to final x is equal to P final x. So initial value is x component is what? This half mu. So half mu plus impulse in x direction is 0 because zt is perpendicular to this, equal to this momentum 0. So we straightforwardly write velocity v is equal to half u. You can see the simplicity by impulse momentum principle, simplicity as well as only solution. Now impulse momentum principle for y direction. In y direction you can see, say this way. So in y direction this is impulse and this is, so that is how we can write here. P initial y component summation I to final j y component and P final y component. So this is minus root 3 by 2 because y we are taking in this way positive. So minus root 3 by 2 mu plus jt and y component of momentum is 0. So you can write here directly what is jt, impulse of tensile force, root 3 by 2 mu. Now this is a typical example of impulsive event. Here you cannot apply Newton's second law during the process the string is becoming taut. Again there is one idea which is remaining to discuss in detail, that is properties of elastic string and inelastic string. Actually we have taken elastic string and we have assumed here that this particle will move on a circular path, but we have to analyze it. Now we discuss behavior of inelastic and elastic strings during such impulsive events. That is this is very important discussion because usually you will find in your textbook problems they will not mention, they will mention simply string, and you have to assume it is inelastic, perfectly elastic. But when you do such kind of experiment, you'll not, this kind of behavior will not be observed. What we observe, when the string becomes taut, this ball will go in this way, not on a circular path. So you'll get have some confusion. But in textbook problems, we are usually assuming idealized situation. So what is the idealized situation here? Let us first discuss here behavior of inelastic and elastic strings during such impulsive event. One more thing. Here in this problem, I have mentioned earlier that we can obtain solution by graphical method also, means geometrical method also. So before we discuss the properties of a string, elastic and elastic, let us see how we can apply the geometrical method. Geometrical method or graphical method. In the present problem, the magnitude of initial momentum, mu vector, and angle between mu vector and impulse jt of the tensile force and the angle between vectors jt and the final momentum mv vector are known to be 30 degree and 90 degree respectively, because with the help of this impulse moment diagram you can see here that is the jt direction this and this angle 30 degree, and this jt you can see this angle 30 degree and this angle 90. So the angle between jt and mu final momentum is 90 degree and this angle is 30 degree. These angles are known, so we can construct a triangle based on triangle of vector addition. Therefore the impulse momentum equation mu vector plus jt vector is equal to mv vector can be represented by a geometrical construction as suggested by triangle of vector addition. So we draw this mv vector, then jt vector, and the resultant mv vector will be from tail of this point to tip of that point in this way. So MV vector. At angle 30 degree, we draw JT vector. So this is what, and from here we draw the MV vector in such a way that where it meet, this angle will be 90 degree. So this inner angle will also be 90 degree. And from this triangle, you can easily write the answer. You can write here, MV will be MU sine 30. So MV is equal to MU sine 30. So V is equal to U by 2. Similarly, from here, JT is equal to MU cos 30. So you can write JT is equal to MU cos 30 or root 3 by 2 MU. So in some situation, by drawing this impulse momentum triangle, you can also find simpler solution. Again, I'll leave you. So, and again, where this will provide simpler solution, particularly in two-dimensional problem. So whenever you find you have leisure time, try to practice this method also, because sometimes this method will provide you very simple solution. And particularly when we analyze collision in center mass frame, at that time this kind of diagram will provide simpler solution. So I'll recommend you to keep in mind, you have to learn this method also. Now we come, as I promised you, that to discuss the behavior of elastic and inelastic strings during an impulsive event. Remarks: behavior of inelastic and elastic string during an impulsive events. Why I am calling remarks? Because these are very fine concepts which you have to understand. Say that the situation we will draw here. So this was the initial momentum. It was the direction of a string, and plus JT, and that is what? Final momentum. So that is again impulse momentum diagram we had drawn. So it will help us to understand the ideas. So what we proceed here, X and Y component. Again, this component root 3 by 2 MU, this component half MU. Consider the transition process that starts from the instant when the string becomes straight and ends when the particle begins to move on the circular path. Duration of this process is negligible as compared to the time interval required to cover a finite observable distance by the particle. Here, this is very important. Why I am saying that duration of this event is negligible? Because of that. Duration of this process. What process? This process starts from the instant when a string becomes taut to that instant when the particle begins to move on the circular path. Duration of this process is negligible as compared to the time interval required to cover a finite observable distance by particle. So the time in which you see the motion of particle from one place to another place, with any observable time interval, this time interval of this event is negligible. So we can call it an impulse event. In this transition process, a part of kinetic energy that is due to component of momentum along the string goes into the deformation energy of the string. But due to inelastic nature of the string, deformation is not recovered at all. Therefore, all this kinetic energy and corresponding momentum component is lost. That is the important idea. Actually, during this process, the string will be lengthened. Of course, this extension spring, that is called deformation, is negligible as compared to length of string, so it will not be visible, but there is deformation. So this component momentum along the string and kinetic energy corresponding to this component momentum will go into deformation energy. Again, the string is perfectly elastic, so this deformation is not recovered at all. So it will not push the ball back. So all of this kinetic energy and this momentum is lost. So that is what? Due to perfectly inelastic nature of the string. But what will happen if the string were elastic? We'll discuss it again. In case of an elastic string, elastic means perfectly elastic or somewhat elastic, a fraction or all of its kinetic energy that goes into deformation of the string will be recovered depending on the degree of elasticity of the string. For a perfectly elastic string, all of this kinetic energy will be recovered with the momentum component reversed. So that is again, if it were given that the string is perfect elastic, so what we can take here, after the string becomes taut, this momentum will remain there, but this momentum will get reversed because all this energy corresponding to this momentum will be stored in the spring and then it will reverse back and it will be recovered. So this momentum will be recovered in reverse direction. And again, depending on degree of elasticity, suppose the string were not perfect elastic, so whatever the kinetic energy is absorbed here of this momentum, that will not be recovered in reverse direction fully, it will be recovered partially. So if you do this experiment at home, what you'll find, this ball will move that way. So this moment will be reversed with reduced magnitude, because again, as we cannot have a perfectly elastic string, we cannot have a perfectly inelastic string also, but we have a string which is partially elastic, partially inelastic. So we have to reconcile our daily experience with the ideas explained in textbooks. Actually, in textbooks, usually ideal conditions are discussed. So usually we discuss a problem where the string will be either perfectly elastic or perfectly inelastic. But later I will discuss here some situation where the string will have partially elastic properties. The momentum component perpendicular to the string and corresponding part of kinetic energy remains unchanged because the string tension always remains perpendicular to this component of momentum. Actually, during this transition process, every time the tension T is perpendicular to this component of momentum or this component of velocity. So this tension will cannot reduce this component. So this component will remain unchanged and corresponding kinetic energy of this component will remain unchanged. So that was idea. I have explained you how an elastic string will behave during an impulsive event, and we'll just conclude today's talk and let us decide some homework as usual. Home assignment today, actually I will not give you any particular problems to solve. This idea is to revise what we have discussed today. Revise all the ideas and examples discussed today in this lecture, because what idea we have studied today, they will make basic building blocks of this method to analyze further. Actually, further we have to analyze conservation of linear momentum and collision problems in this way. Thereafter, we discuss application of impulse momentum principle on system of particles. At that time, we discuss center mass and how idea of center mass will help us to analyze the problems we'll discuss at that time. So again, thanks for patient listening. We meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which are or seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.